You check if it's fine. So I'll share my screen. Is it visible? If you can, I think if they off the lights, it would be better. If they switch off the lights. Better, right? How are you? Everything good? What courses are you doing this semester? Just one? Just this? Wow. You have all the time on earth. Just no. Oh, really? That's interesting. Okay. Yes, yes, they are my classmates. Oh, Central Bank. Wow. So all the central bankers are coming. Sorry, guys. What was happening to? Okay. Nigauja told me some of you are still facing difficulties with hypothesis testing, right? Is anybody who is facing difficulties with hypothesis testing? Significance test? Okay, no problem, but you are getting used to, right? You watch the previous videos. Okay, today I'm going to try as much as possible to start from scratch and do, because she told me some of you are facing difficulties with hypothesis testing, which I was surprised, because I know, except you, I know with all of you, we did it last semester in Bank 504, so I don't know. And yes, so I'll quickly go, we did last week, I'll quickly go over simple regression. Then we'll do multiple regression. Just telling you what we'll do. Then we'll see interpretation of coefficients. Before interpreting coefficients, we are going to do hypothesis testing. Then we can look at things like goodness of fit measures. What else can we look at? I think that is it, yeah. Because she said we should not do diagnostic test. You haven't done it yet, right, with her in class? Heteroscedasticity, multicollinearity, you haven't done it. Okay, so we can see these kind of things. I'm talking of this course. This course. You did last semester, that was a different course. I'm talking of this course. You haven't done it yet. Okay, so we are going to use the same data. Where is the data? Okay. Why are you laughing? Everything fine? Are you going to Iran this summer? You have to. You must go to Iran. You must. We are going to make sure you go to PAP. You have to go back to your country. We no longer want. We, we no longer want you here. You have to go away. Take your dog and go back to Tehran. Okay, guys. We have 3 variables. This is our data, right? I'm trying to explain everything from scratch. You know all this, but I just want to try and explain. So I make sure nobody has problems. Because I can assure you, ordinary least squares is the basic thing you will ever know in econometrics. Once we start doing co-integration and error correction models, I'm not saying they are difficult, but they are more advanced than this. Just know that. So we have GDP, we have CPI, and we have trade openness. Of course, you know GDP is proxy for economic growth. CPI is consumer price index, proxy for inflation, and trade openness shows the openness of a country to international trade, right? That is exports and imports percentage of GDP. So we have these 3 variables, we have their data from 1996 till 2018. By the way, guys, this is time series data, right? Because it is data for a particular subject, just one country, for a number of years. Okay. So first, I'm going to input this data into eViews. We are going to start with simple regression. Now, what's the difference between simple regression and multiple regression? With simple regression, we have just 2 variables, one dependent and one independent, just 2. With multiple regression, we have more than 2. It can be 3, 4, 5, any number, but more than 2. One dependent and more than 1 independent. So for simple regression, we are going to take GDP as dependent and CPI as independent, just these 2, right? So now I'm going to import the data to eViews. I'll open eViews. I should use eViews 10. You can use any one. I have 10 and 12, but I like 10. It's better for me. So here, if it is cross-sectional data, we will take unstructured, undated. If it is time series data, we will take regular frequency dated. If it is panel data, we will take balanced panel. But like I told you, it must be a balanced panel. Because if the panel is unbalanced, then we cannot use eViews. We have to use data. I told you what balanced panel and unbalanced panel are. So I hope you know that. For balanced panel, all cross sections have the same time span, right? So dated regular frequency. Of course, it's annual data, right? Because it's every year. So it is from 1996 till 2018, right? Oh, sorry. 1996 to 2018. Now, here in the, I just have to type in the command, right? So I'll type data, GDP. I'm just type, the command is data, give a space, and then just put the variables. Always start with dependent variable. GDP, CPI, trade openness. Once I press enter, you see the spreadsheet opens. Now I just have to copy my data from Excel and paste on eViews. You know all of this. So I'm going to copy just the variables, by the way, just the numbers. And I'm pasting on eViews. Paste on the first cell here, very first cell. And then you can close this. It doesn't matter because the data is there. You see this is CPI, GDP, trade openness. You can check to see if the data is actually there. For instance, if I click CPI and I press enter, you see I have the data, right? This is my data. And if you see a last updated 12:52, look at my time here, 12:53. So you know that you're on the right track. You can check the data of all of them at once, CPI, GDP, just click one, hold control, click the other. Then you can just press enter, all of them will open. So these kind of things. So once we have the data here, Now, there are many things we can do with this data. We can check the graphs, we can check the correlation metrics, we can check descriptive statistics. You know how to do this. I explained in previous videos. Go back and watch it. But just to do a favor, maybe you want to watch this video, I will just show you. So I'll click GDP, CPI, trade openness. I press enter. Come to view. View. And here you can check graph, you can check descriptive statistics, and you can check correlation metrics under this covariance analysis. If you are trying to check graph, just click on this graph. Don't change anything, just come here, change this single to multiple. The reason why we are choosing multiple is because we want all the graphs to be in one place. Because okay, let me show you single. Let's say single. If I put single, you see how it is. It draws the graph for all the variables in one graph. So you see, here is GDP, here is CPI, here is trade openness. It's giving you a single graph for all three of them, but that's not what we want. We want to see individual graphs. So that's why we use multiple. So instead of single, I'll use, what's happening? Change this single to multiple, and you see it gives us 3 different graphs for each variable, and we can interpret the graphs, right? Again, how do we interpret the graphs? Always interpret the graphs from the perspective of dependent variable. What do I mean by dependent variable? The dependent variable depends on what happens to the independent variable. So you have to say, this is happening to independent variable, and it is causing this to happen to dependent variable, and not the other way around. For instance, what's dependent variable here? GDP, right? So if we want to interpret the effect of CPI on GDP based on these graphs, what we are saying is that CPI has an average upward trend, and GDP also has an average upward trend. Therefore, we expect positive relationship. So based on this graph, we expect an increase in CPI to also cause an increase in GDP. But you cannot say an increase in GDP causes increase in CPI. Because if you are saying that, it means you are trying to say that CPI is dependent variable, which is wrong. Because you know the dependent variable depends on the independent variable. Okay, you know all of these things. Same thing with trade openness. Trade openness has an average upward trend. GDP has average upward trend. So on average, we expect positive relationship. Increase in trade openness is causing increase in GDP. So based on these graphs, we are expecting that both CPI and trade openness should each have positive effects on GDP. So you can explain your graphs that way, right? Okay, we should check descriptive statistics. Again, with descriptive statistics, by the way, from here, you can just go to view, descriptive statistics. You can check common sample, individual sample. If you have the same number of observations for all variables, then either one will give you the same results. Like let's say, by the way, you see here we have 23 observations. So if each of these variables has 23 observations, which is the same, which is like our case, then it doesn't matter. It doesn't matter whether you take common or individual sample, it will give you the same thing. But if there is a case where one variable has more observations than another, then if you take common and individual samples, you will have different results. Why? Because if you take common sample, it will try to equalize the variables. So for instance, if one variable has 25 observations, another has 20, and another has 15, then it will give you results for 15. It will try to give you an equal result. So it will consider just 15 observations for each of them, common sample. But if you take individual sample, then it will look at each of them individually based on their respective sample sizes. So it's always, I don't know, for me, I always take common sample, but it depends on you, the researcher. You can take either one. But why I always take common sample, it doesn't matter for me anyway, because my data always have the same variable, and all my variables always have the same number of observations. Okay, so I'll take common sample and we have our descriptive statistics. Now, in these descriptive statistics, there are some interesting things we can explain. You can talk about the mean, the median, the maximum. In fact, you can talk about all of these things. Like you present it in your research paper or your thesis or whatever. By the way, you can copy this and paste on web, right? You can just take control, copy, then you can copy and paste on web. But when doing a research, when writing an article or in your thesis, some of you will be doing your thesis next semester, some of you are doing it this semester. Okay. You should not copy data and paste. Create your own tables. Like, let me tell you what I mean. Copy. I'll show you something. I copied just one variable. Okay, let me copy all. So copy all. I'll tell you what I mean. You see, this is descriptive statistics, but you cannot paste, you cannot use this table in your paper or in your thesis. It's not acceptable. You cannot copy and paste. Okay, you can copy graphs, no problem, but with tables, you have to create your own tables, and there is a standard of creating tables. And the best way for you to know how to create tables is by looking at sample articles. You can check from the literature, check some sample papers, see how they create tables, and follow that format to create your own table. Then you can input this data, right? For instance, I will show you one of my articles. Let me see how I created my tables. If for your information, anyway. By the way, guys, this is an article I wrote with Kohan Hoja, so it's quite interesting. Okay, I think I should show you on as PDF, maybe on web you will not see it well. The Muslims, where are the Muslims? Why are you fasting now? Last time you could not fast because you were not feeling fine, but now you're feeling fine, so are you fasting? You're just laughing. Are you fasting? You're not answering, you're just laughing. You should fast though. You are Muslim, you should fast. Because you have to fast, you are Muslim. Though you Muslims cannot eat, but we Christians can eat, so you should bring your food to us. Funny, right? Yes. Okay, you see, you can paste graphs. You can copy your graphs from eViews and paste, no problem. But with tables, like you see correlation metrics. Okay, I'll show you, but let me show you descriptive statistics. This is unit root. Where is descriptive statistics? Okay, guys, I have so many tables here. It's my descriptive statistics. I don't have it. Okay, fine. Look at something. Why do I have so many things open? Sorry, guys. My laptop is messing up. Okay, look at this is descriptive stat. You want to go? Why? Are you fasting? You're fasting? You're not Muslim. Okay. Then you're hungry. You want to go and eat something. Okay. No problem. It's okay. You can. Yeah, you can go. You watch the record. Okay. Okay. And take very good care of your dog, right? So you see, this is the descriptive statistics I copied from eViews and pasted, right? You see how it shows. But if I'm trying to write a paper or my thesis, I copy, you see, I try to draw the table, try to draw my own table. So basically, this is how, well, this is not the only way, but in most papers, this is how they present tables. So if you see lines, you have border lines around the headings, like a line above and a line below, and then in between there are no lines, no table lines. It's just empty, and then you have one line at the end before you put some notes. So typically, this is how they do tables in research papers, in articles. Let me show you other tables. So you can copy graphs anyway. You can copy graphs and paste. So you see, like with correlation metrics, you just have some two border lines above the headings and then below, but in between there are no lines. So typically in this is unit we'll see later. Okay, you see here you have some. So if you check research articles, research papers, you see how they are drawing their tables and you can follow suit, right? Okay. So that was just for your information anyway. So you can copy your results and paste and try to interpret it. Of course, you know how to interpret these things, right? You know what the mean is. The mean is the average value. Like for all the observations, if you add all the observations and you divide by the number of observations, it gives you the mean. The median is the middle value where you arrange the observations in either ascending or descending order. Arrange them, and the middle value is the median. The maximum simply means the highest value. The minimum is the lowest value. What's the standard deviation, by the way? Yes, the standard deviation, it shows us the dispersion, how dispersed are the data away from their mean value on average. Are you going? Okay. Everybody wants to go? You two, are you going? Okay. It's like everybody will go and I'll remain alone. No problem. They can watch the record. Okay. So the standard deviation is showing you the dispersion, how dispersed are the variables, the data points away from the mean. The skewness. What's skewness telling us? Ketosis, skewness. Any idea? If I can draw something on the board. Actually, skewness and ketosis are telling us about the shape of the distribution. Is it the same as that of a normal distribution or is it different from a normal distribution? Because for a normal distribution, skewness will be 0, which means it has no skew. For a normal distribution, ketosis will be 3, right? Now, if you have skewness which is more than 0, either positive or negative, then it is skewed. So if it is above 0, positive, it is positively skewed. If it is below 0, negative, it is negatively skewed. But if it is 0, it is normal distribution. For ketosis, if it is 3, it is normal distribution. If it is above 3, it means we have excess ketosis. If it is below 3, it means we also have excess ketosis. But now, if it is above 3, it means we have positive excess ketosis. If it is below 3, it means we have negative excess ketosis, right? If it is positive excess ketosis, there is a word we call it. We say it is, guys, ketosis. Let's spell it. ketosis equals 3 for normal distribution. Normal distribution. Now, for this normal distribution, if the ketosis is 3, which shows that it is normally distributed, then we say it is mesoketic. Mesoketic, right? But if ketosis is bigger than 3, right? It means we have positive excess ketosis. We say it is platyketic. Platyketosis, that's a term. If ketosis is less than 3, we say there is negative excess ketosis, and there is a word for it. I forgot. I will just search now and tell you. Just give me a second. Excess ketosis. Okay, I think hold on. No. Okay, give me a second. I will check. I wrote it down somewhere. There's 614. You know, these terms at times, guys, too many things open in my laptop, so I'm sure the other guys did not come because they know it's regression. Regression is easy. That's why they didn't bother to come. Just a second. Okay. Okay, it's the other way around. So if it is negative excess ketosis, it is platyketic. Can you see? Yes. But if it is 3, which means it is normally distributed, then we say it is mesoketic. Mesoketic. Then there is another term, another word. I don't know. Positive. Are you even supposed to know these terms? Are they too important? Okay, leptoketic. I got the term. I forgot. So guys, if ketosis is 3, which means it is normal distribution, we say it is mesoketic. If it is bigger than 3, that is positive excess ketosis, it is leptoketic. And if it is less than 3, negative excess ketosis, then we say it is platyketic. Whatever, it doesn't matter. So just know that skewness and ketosis are giving us an idea of the distribution of the data, right? But to formally test if it is normally distributed or not, we use a statistical test, which is the Jack-Berra test. This Jack-Berra test. And to do the Jack-Berra test, what's the null hypothesis for Jack-Berra test? Jack-Berra normality test. What's the null hypothesis? Data is normally distributed. What's the alternative hypothesis? Data is not normally distributed, right? Okay. So we are going to do this test by checking these probability values. I'm going to talk about it today, hypothesis testing. Since Nigaoja told me you are facing some difficulties with hypothesis testing, I will spend some time to talk about it. But for now, let me just explain. Check these probability values. If they are bigger, that is, we should use 3 significance levels. We have 3 significance levels we can use. We have 1%, 5%, and 10%. These percentages are our significance levels, right? We call them alpha, but they are significance levels. They call them alpha. So it depends which one you want to use. Are you using 1% or 5% or 10%? Generally, they use 5%. If you're using 1%, it means you're trying to be too cautious. If you're using 10%, it means maybe you're trying to be too considerate. But generally, they use 5%, right? How do they use these significance levels? You check the probability values. If your probability value is less than the significance level, the one you're using, let's assume that we are using 5. So let's say we are using 5% significance level. 5%. If the probability value is less than this 5%, what do? If probability value is less than significance level, what do? No, less than, not greater than, less than. Probability value is less than, we reject. If it is less than, yes. If probability value is less than alpha, that is less than significance level, then you reject the null. And if you reject the null hypothesis, then you have to accept the alternative. What I'm telling you is that if you reject something, you must accept another thing. But if you cannot reject it, then you don't even look at the other one. There are 2 things involved. Like, I have 2 things. This, my left hand and my right hand, right? If I reject my left hand, then I accept my right hand. But if I cannot reject my left hand, then I should not even look at my right hand because I cannot reject this one. I fail to reject this, so I'm not even concerned with what is happening here. If you reject the null hypothesis, then you have to accept the alternative hypothesis. But if you cannot reject the null hypothesis, then you cannot even look at the alternative hypothesis, right? The one thing I'm going to insist on, and I insisted last semester, is that we never accept the null hypothesis. The only time you should even use the word accept is when you're talking about alternative. And you can only accept the alternative if you reject the null, right? So if you reject the null hypothesis, then you can accept the alternative. But if you cannot reject the null hypothesis, then you don't even look at the alternative hypothesis. But don't say that because you cannot reject the null, it means you are accepting the null. No, you never accept the null. It's either you are rejecting the null or you cannot reject the null. That's it. Okay. Now, when do we reject the null? We reject the null if the probability value is less than the significance level. But if the probability value is greater than or even equal to the significance level, then we cannot reject the null, right? So let's perform the test. So that's how we perform hypothesis testing, using probability value. We can also do it using test statistic, which I'll tell you. So let's perform the test, the Jagbera test. Now, looking at this probability value, 0.6, this is 60%, 0.6. It is bigger than 5%, right? Therefore, if it is bigger than 5%, it means we cannot reject this null hypothesis. We fail to reject the null. What is the null? The null tells us that the data is normally distributed. If you fail to reject that fact, what does it mean? It means that the data is normally distributed, right? But if you reject it and you accept this, it means the data is not normally distributed. But because we cannot reject the null, I'm not saying we are accepting it. I'm saying we cannot reject it. We fail to reject it. Therefore, it means we are concluding that it is normally distributed, right? So that is how we perform Jagbera test. Here is 0.4. Again, we cannot reject, so it is normally distributed. Here is 0.3. Again, we cannot reject, so it is normally distributed. So based on this Jagbera test, looking at the probability values, we conclude that the data of these three variables are normally distributed. So that's how we perform hypothesis testing. So yeah, that's all you can interpret. All these other ones are not too important. So that is descriptive statistics. Okay, now I'll show you correlation metrics. Again, come to view, come to this covariance analysis, change this covariance, untick it and choose correlation. Why are we doing that? Because we are trying to check correlation metrics. You know, there is a difference between correlation and covariance. They are similar, but there is a difference. Correlation is like a standardized version of covariance. Anyway, don't bother too much about that. At PhD level, you will understand better, but just know that correlation is standardized version of covariance, right? So we are checking correlation. So initially, this one was ticked. Untick it and take correlation and press enter. You have correlation metrics. Now, before interpreting these correlation metrics, I will let you know that the correlation matrix is symmetrical. What do I mean by symmetrical? It means, look at this leading diagonal. This is, are you seeing here 1, 1, 1? Above and below the leading diagonal, we have the same values. This is 0.97, this is 0.97. This is 0.93, this is 0.93. This is 0.95, this is 0.95. So once you have the leading diagonal, the values above are the same as the values below. So typically, if you're reporting your correlation metrics, no need for you to report above and below because it is the same values. That's why typically I'll show you, like if you see the paper we did, where have I done correlation? You see my correlation metrics, I just reported the ones below. This is, the diagonal matrix will always be 1, 1, 1. The diagonal, leading diagonal, will always be 1, 1, 1. Above and below is the same. So no need to put the same things. So you see here, I just put the values below. This above, nothing, because it's the same, right? Okay. Now, how do we interpret correlation metrics? Correlation metrics actually is showing us correlation. So all these things are correlation coefficients. They call them Pearson correlation coefficients. I'm sure the person who introduced this thing is called Pearson. I don't know. Pearson correlation. So you see, they call it Pearson correlation coefficient. Maybe it was introduced by somebody called Pearson. I don't know. But for short form, we just call it correlation coefficient, right? So these are correlation coefficients. Correlation coefficients show us what do they show us? They show us linear relationship. Linear means straight line. Linear relationship. Now, what do I mean by a linear relationship? Okay, straight line, of course. Like, in particular, they show us the strength. Strength means degree. Strength and direction of linear relationship. Strength, I'm insisting on these two words, strength and direction of linear relationship. What do I mean by strength? By strength, I mean, is the relationship weak? Is it medium? Or is it strong? Right? Strong / powerful. I will tell you why I included powerful. But just say, is it weak, medium, or strong? By direction, what do I mean? By direction, is it negative or positive, right? Negative or positive. But it is linear relationship. Now, if it is negative or positive, you will just know. Because if you see negative sign, it is negative. If you see positive sign, it is positive. Okay. But then, for the strength, how can we know if it is weak, medium, or strong? If it is weak, it will be less than 30. The correlation coefficient is less than 30%, that is less than 0.3, less than 30%. Less than 30%, then it is weak. If it is between 30 and 70, right? 30% and 70%, medium, right? If it is above 70%, then it is strong, right? Okay, I added here powerful. Why am I adding this powerful? The reason I'm adding this powerful is because I want to let you know that it can be strong, but it is not powerful. Powerful means very strong. And we use this powerful when talking about multicollinearity. We will see it later. So, for instance, if it is 70, let's say it is 75%, we will consider it to be strong because it's above 70, but it is not powerful. So we start looking at powerful when it's above 80, 85, when it's, of course, 90 is powerful. But if it is above 80, 85, we can say it is powerful. But above 70, we can say it is strong, right? For correlation, we are not interested in whether it is powerful or not. If it is strong, it is strong. But when we'll be checking multicollinearity, then we will tell you that it has to be powerful. So which means if it is 75, of course it is strong, but it is not powerful. So we cannot say there is multicollinearity. So just have it in your mind that powerful is maybe 80, 85. The strong is above 70. Okay. Now, how do we interpret that? I will copy this data and just paste so we can interpret it together. I decided to do everything today from scratch. So I want to make sure you know everything, because most probably at some point we'll be done with regression and we'll start doing other things like panel data, time series data. Okay, so now look at this 0.97. What is this 0.97? It is the correlation coefficient between GDP and CPI, right? 0.97 is 97%. So which means it is strong. Of course, it is powerful, but it is strong. We are not talking about powerful here. It's either weak, medium, strong correlation. So it is strong. Is it positive or negative? Positive. So what we'll say is that there is a strong, positive, linear relationship between GDP and CPI. So there are three things you mentioned. You mentioned the strength, the direction, and then the fact that it is linear. Is it strong, positive, linear, or is it weak, negative, linear, or is it strong, whatever? It can be weak, negative, linear, or it can be strong, positive, linear. I don't know. But you understand what I'm trying to say. So by the way, look at all these guys, 0.97, 0.93, 0.95, 0. So they are all strong and they are all positive. So you can say all the variables, like you can say GDP has a strong positive linear relationship with CPI. GDP has a strong positive linear relationship with trade openness. CPI has a strong positive linear relationship with trade openness. These kind of things, right? Okay. So if here was negative, let's say I put here negative, then we would have said strong negative linear relationship. If it was between 30 and 70, then we'll say medium. If it was less than 30, we'll say weak. Okay. Since we are talking about correlation metrics, I will just mention multicollinearity, but we are not seeing it now, but I'll just mention it. What is happening with multicollinearity is that multicollinearity is one of the assumptions of ordinary least squares. We'll see it subsequently, maybe next week. But multicollinearity is a problem where there is a powerful linear relationship among the independent variables, regressors. Okay. The issue now is that with multicollinearity, we don't include dependent variable. We look at only the regressors, right? Only the independent variables. If they have a not strong, powerful. If they have a powerful linear relationship, then we say there is multicollinearity. And by powerful, it should be like above 80, 85, getting to 90. Okay. Anyway, correlation metrics is not the only way we can use to check multicollinearity. We also have things like variance inflation factor, tolerance factor, auxiliary regression. We'll see them anyway. So I just said I should mention it there. That is it about correlation metrics. So now we are going to run a regression. By the way, you didn't want to come today? What? Ah, you were busy with the department.
No, I was paying my debt.
You were paying your debt? Why are you a debtor? You are owing debt? You are supposed to be locked up, you know. All debtors have to be locked up in the police cell. Are you also a debtor? That's not possible. Why is the school owing you? What happened? So you give loans to the school? They borrow money from you and they pay you interest? You might be a central bank. You know? Okay, guys, let's run a regression. Okay, so we are going to start with simple regression, right? So GDP, by the way, all these variables are in their level form. I did not convert to log. You know how to convert to log, and you can do it, right? I don't have to do it. Because I showed you last class, it's in the video, watch it. I'll use level data. But it's always good to use log. Okay, let's use log because it's easy for interpretation. Generate lane GDP equals log GDP. So I can just change this GDP to CPI and I change CPI. Openness, and I change trade openness. Okay, so we are going to use logs. You know, it's taking the log, by doing log transformation, there are many advantages. It's easy for interpretation because we can express everything in percentage. Also, it rescales the data, it reduces the variability, and it tries to solve some of these problems. Like if If the data is not normally distributed, it might help. It might try to solve heteroscedasticity problems. You know, it's always good to use log. Okay, so we are doing simple regression now. Our dependent variable is GDP, so we'll take lean GDP. And let's take lean CPI. There are many ways we can do regression, but I will show you 2 ways. I can, by the way, it's always good to start picking with the dependent variable. So I'll pick lean GDP, hold control and pick lean CPI. If you select both of them, I can just right click on my keyboard, come to open, take open as equation. It takes me directly here. But the constant, it doesn't matter whether the constant is at the end or at the beginning. At the end of the day, it's still a constant, right? So you can leave the constant at the end, or you can put it, you can remove it from, oh, I ran the regression, sorry. Or you can remove the constants. It doesn't matter anyway. You can either leave this constant here, or you can remove it and put it here. But it should always be after the dependent variable. Dependent variable is first, then constant independent variables, or dependent variable, independent variables, constant. So the constant can be anywhere, but it should, the dependent variable should always be first. Then you can just click OK. Or if you don't want to use that method, what you can do is come to quick, come to estimate equation. Then here you have to manually type in the variable. So lean GDP, constant, lean CPI. I'm not including trade openness because I want to do simple regression. You know, simple regression has just one dependent and one independent, right? So I'll click OK. Don't change anything here. You see here the method is least squares. This NLS ARO MA is actually ordinary least squares. Don't change it because we are doing ordinary least squares, basic regression. Later on, when we will start seeing ARODL, autoregressive distributed lag models, you will discover that we will change it and take this ARODL. At PhD level, when you will be doing co-integrating regression, things like fully modified ordinary least squares, dynamic ordinary least squares, CCRO, you will take co-integrating regression, but anyway, no bother for now. So least squares, ordinary least squares, don't change anything, just click OK. We have our regression output, right? This is our regression output. You check, you see a dependent variable is GDP, our method is least squares, and we have 23 observations. Okay. Our constants and CPI, right? Now we can interpret these coefficients. But before interpreting any coefficient in statistics, you have to make sure it is statistically significant. So you have to check the statistical significance. How do you check statistical significance? You have to perform hypothesis testing, right? So now, before we interpret these coefficients, we are going to perform a hypothesis test. I showed you hypothesis test before when I was looking at Jagbera. Now I'll formally tell you about it, since we have this opportunity about hypothesis testing. Okay. Hypothesis testing. By the way, why are we doing hypothesis testing? Why? We are doing hypothesis testing because we want to draw inferences about the population from the sample. What do I mean by that? If you're carrying out a research, you don't have the whole population. You have just a sample. But you want to use this, your results from your sample, to generalize about the population, right? For instance, let's say I'm carrying out a study about banks in North Cyprus. Let's say in North Cyprus you have thousands of banks, just an example. But I don't have data for all these thousands of banks, right? I can collect data for like 500 banks, a big enough sample, which is representative. I don't have data for all the population, all the banks, but I collect data for like 500 or 300 or 100 banks. The sample should be big enough and it should be representative. Then I do some statistical tests and get the results. Now, these my results are results for my sample. But I'm trying to do policy implications. I'm trying to draw conclusions about the population, right? So if you're trying to draw inferences about the population using your sample, then you must make sure that you must do hypothesis testing. It is this hypothesis testing that will allow you to draw these inferences about the population from the sample. Okay? Are you sure you're with us? Maybe you're thinking about your debt. Are you thinking about your debt? Okay. Ikra, you're on TikTok? I saw you on TikTok. Facebook? I bet. What are you doing on your phone? You are enjoying your social media and everything. These kind of things are very easy, so you know everything. So okay. Okay. You did hypothesis testing before? Your thesis. What was your thesis? Sorry?
Was in Turkey.
Okay, in Turkey. I understood.
It's about the debt, but the unpaid one.
Unpaid debts?
Yes, on bank.
Unpaid debts in the bank?
Yes.
Creditors defaulted.
No.
The bank did not pay its debts, or the bank loaned out money to creditors and the creditors defaulted. I mean to borrowers and the borrowers defaulted.
It's about the unpaid debt, about persons.
Okay, individuals borrowed money from the bank
Yes.
and they did not pay.
Yes.
Non.
About sectors, all.
I think.
I have the variables because
I think there's a term they call it in. I think they call it non-performing loans, something like that.
yeah.
Okay, it's fine. Let's continue, guys. Hypothesis testing. Now, with hypothesis testing, sorry, guys, I'm getting a little bit confused. With hypothesis testing, we can do it in two ways. Who can tell me? Two ways we can do.
Statistics and probability. Statistics and probability.
What's the difference between them? Between
the significance of level and the interpretation is different.
Like if we are trying to do hypothesis testing, there are two ways we can do it. How can we do it?
There is the rule of thumb, which we use it in these statistics, and there is the hypothesis null and in the probability, which is the significance level, 1%, 5%, and 10%. If you have anything, you can add it.
No, I think, is that all you have to tell me? Like, we can use the T statistics, we can use the test statistics, and we can also use a probability value. But what's the difference? That's what I'm asking. All of them will give us the same results, most probably.
Yeah.
But what's the difference? Trying to check your notes. Okay, you can check. Okay, I'll tell you what I'm trying to ask you. Test for significance. Okay, don't bother, don't bother. Okay. Now, while doing hypothesis testing, there are two methods. You know, I just noticed I did not mention this last semester. That's why I was getting surprised. I did not mention it last semester. Okay. To do hypothesis testing, we can either do significance test or confidence interval. I mentioned just test for significance, right?
Yes.
No problem. So we can do significance tests or we can do confidence interval. Two ways we can do hypothesis testing. But generally, either way gives you the same results. It's not like you have different results. the same results. But generally, we like using, most people like using significance test for significance, right? So with test for significance, we can use either probability value or test statistic. Did I spell it well? Okay, I'll tell you, this hypothesis testing is very important, so you should pay attention to it. Why is the time flying? So time is getting, okay. So before coming to confidence interval, let's talk about statistical test. Sorry, significance test. With a test for significance, we are using probability value or test statistic, right? If we are using, okay, let's say probability value, and let's say test statistic. Now, with probability value, right, we have 3 significance levels. 3 significance levels. As you know, we have 1%, 5%, and 10%. Okay. What are we doing? We are going to check the probability value that we have, actually the probability value of the test statistic, but we'll check our probability value. If our probability value, okay, is less than our significant, actually these significance levels, they call it alpha. At times they call it alpha, but it's significance level. If probability value is less than significance level, then we reject the null hypothesis, right? If prop value equal to significance, did I spell it well? Significance level, then we fail to reject the null. We never accept the null. We fail to reject the null. Yeah, we reject the null and accept the alternative. So if you reject the null hypothesis, you accept the alternative hypothesis. But if you fail to reject the null, you are not accepting the null. You fail to reject it, then you don't even care what is happening to the alternative. So this is how we make the decision using probability value. First, you should decide your significance level. Most of the times they use 5%, but you can use 1%, you can use 10%. You can use all 3, but it's good to use 1. Most of the time they use 5. So let's assume we are using 5. If our probability value is less than 5%, then we are going to reject the null hypothesis. And since we are rejecting the null hypothesis, we are going to accept the alternative hypothesis. But if your probability value is greater than or even equal to significance level, then you fail to reject the null. You don't accept the null. You fail to reject it. And you don't care what is happening to the alternative hypothesis. Okay, so that's how we are using probability value. Now, we can use test statistic to perform this same test of significance. We can use test statistic. With test statistic, we have 2 things. We have the test statistic, we have the critical value, right? If test statistic is greater than critical value, then we reject the null, and accept the alternative hypothesis, right? If statistic is less than critical value, then we fail to reject the null. So look at, people get confused with these things at times. It's very easy, you don't even need to cram. If you are using probability value, then if you want to reject the null, it should be less than. If you're using test statistic, if you want to reject the null, it should be greater than. So look at, so, good question, I'll tell you. Now, so you see, before we reject the null for probability value, it has to be less than significance level. But for us to reject the null with test statistic, it has to be greater than critical value. So using either probability value or test statistic will give you the same result, right? But at times, there are situations where you cannot use one, you have to use the other. There are situations where you can use both. So you need to know both of them, because if you face a situation where you cannot use one, then you have to use the other. But if you can use both, then either you use both or you use one. It will give you the same results anyway. Now, to check the critical value, of course, probability value will be given to you. Like, look at the test, this result. You see here we have probability value and we have test statistic, right? So probability value will be given to us. We know our 3 significance levels. Test statistic will be given to us. The only thing which will not be given to us is critical value. So if you want to know this critical value, you need to check the distribution tables. For instance, if we are doing t-test, since it follows a t distribution, you have to check t tables. If you're doing f-test, you have to check f tables. But because it is inconvenient to check this table, if you're writing an exam, you don't have the tables with you, right? So it's either you use probability value, or for some of the tests, we use rule of thumb. Like with t-test, there is a rule of thumb. You know, rule of thumb means generally accepted rule. Rule of thumb. What's the rule of thumb for t-test? Critical value is 2. Actually, plus or minus 2. Right? Let me see. How can I write plus or minus? Plus, I'll just say 2 in absolute value. Doing t-test, we don't need to check the t tables. We just know in our mind that the critical value is 2. That is the rule of thumb. Normally, it is around 2. It is not really 2. I can assure you, if you check the t tables, you will see 1.98, 1.96, 1.92. Okay, yes. If you check the t distribution, these are the values you will see for t-test. This 1.98, I think, is 1% significance, 1%. This 1.96 is 5%, and this 1.92 is 10%, right? You discover that all 3 of them, 1.98, 1.96, 1.92, they are closer to 2. So that's why we just say 2 is the magical number. We just take 2 as rule of thumb. Yeah. So you don't need to check the tables for this kind of things. Now, we are going to perform the test. I'll come to the constant. Let's start with this one. Look at this coefficient. We are trying to interpret this coefficient, but before interpreting this coefficient, we want to make sure it is statistically significant. So we are going to perform t-test. So we have t statistic and we have probability value. First of all, let's start with probability value. By the way, before performing any statistical test, you need to know the null and the alternative hypothesis. Because if you don't know this hypothesis, then how can you know what to reject and what not to reject? So, I don't know, where can I write it? Okay, I should write it down here. So t-test, what's the null hypothesis? Coefficient is equal to statistically equal to 0, right? Which means it is insignificant. What's alternative hypothesis? And is statistically different from 0, which means it is significant. So if it is equal to 0, it means it makes no sense. So it is insignificant. If it is different from 0, it means at least it makes some sense. So it is significant. I'm just trying to explain it in a layman's way. I'm not saying that's what it means entirely. Yeah. So just know that 0 means useless. So if you are equal to 0, it means you are useless. It means you are not significant. But if you're different from 0, it means you are a little bit useful, so you're significant. At least it's a trick you can use to know these things without cramming them. Okay. So the null hypothesis is that the coefficient is statistically equal to 0, which means it is statistically insignificant. And the alternative hypothesis is that the coefficient is statistically different from 0, which means it is statistically significant. Okay. We are performing the test. This coefficient, of course, this coefficient is 0.88. It is 0.88. Mathematically, it is different from 0, right? But in econometrics, in statistics, we are not interested in mathematics, but we are interested in statistics. You can be mathematically different from 0, but you are not statistically different from 0. Of course, 0.88 is different from 0, mathematically, right? But we are trying to check if this 0.88 is statistically equal to or different from 0. So we are checking this probability value. This probability value is 0.00, which is 0. Let's say our significance level is 5% we are using. 0 is less than 5%, right? So if 0 is less than 5%, what should we do? Look, if probability value is less than significance level, then we reject the null and accept the alternative. So since our 0 probability value is less than 5% significance level, therefore we are going to reject the null and accept the alternative. So we will reject the fact that it is insignificant, and we will accept the fact that it is significant. Now it is significant. What does it mean? It means that this 0.88 is not only mathematically different from 0, but it is also statistically different from 0. Therefore, we can interpret it. But if it is not statistically different from 0, then we cannot interpret it. So because it is statistically different from 0, we can interpret this coefficient, which I will interpret in a second. So that's how we perform the test. If you try to perform the test with this constant, you'll see that it's also significant, because this guy probability value is less than 5%. Okay, let's try t statistic. Look at the t statistics. 19 and 119. They are bigger than 2, right? Bigger than 2. What does it mean? If test statistic is bigger than critical value, because you know with t-test, our critical value is 2. If it is bigger than 2, then we should reject the null. So you discover that whether you're using probability value or test statistic, you get the same results, right? Are you trying to escape? Are you trying to escape? I caught you trying to escape. Oh, okay.
To get her,
okay. The bank is owing you.
Yeah.
Mm. Okay. See you. You can watch the video. Okay. See you. And make sure you fast, right? Try to fast.
Muslim.
You are Muslim.
Half Christian, half Muslim,
No.
half Jewish.
You have to fast, you know. Okay, guys, so whether we're using probability value or test statistic, we are getting the same results, right? By the way, my friend, are you understanding? You seem.
I'm usually sleepy, but I'm okay.
You too? Sleepy, but okay.
Yeah, I'm sleepy, but I'm okay.
Everybody sleepy?
I'm totally sleepy.
I'm saving my energy until the end of the day.
Okay. We'll be done anyway soon. It's because I started from the beginning to explain everything, because Nigaoja told me you face problems with hypothesis testing. So I just started from the beginning to explain everything to the end. That's why it's taking so much time. Okay. So with test statistic, it should be greater than critical value for us to reject the null. And for t-test, according to rule of thumb, our critical value is 2, right? Guys, by 2, I'm talking of absolute value, because it can be negative, positive, but absolute value. So it should be greater than 2 in absolute value, because you can have negatives as well. Okay. So if you see here, the t-statistics are all positive and well bigger than 2. So, of course, since they are bigger than critical value, we can reject the null and accept the alternative. Therefore, we can interpret the coefficients. Now, that's how we do t-test. How do we interpret coefficients? Guys, if this coefficient was statistically insignificant, then we will not interpret it. What we will write is that, if assuming that this probability value was bigger than 5%, and we do the t-test and discover that it is insignificant, so we will not interpret this 88%, this 0.88. What we will write is that, I'm going to delete some of these things. What we'll write is that lean CPI has no statistically significant impact on lean GDP. As simple as that. You cannot interpret. But because we found it significant, we have to interpret. So how do we interpret? What's the coefficient? 0.88, right? And because we are using lean, log, so we express everything in percentage. So what we'll say is that, so I'll take this off. We'll say is that 1% increase in lean CPI will cause 0.88. Don't try to change it to percent and say 88%. Use the figure exactly the way, because at times some students will say this 0.88, so they will say 88%. No, it is exactly the way it is there. So it is 0.88. So 0.88% increase in lean GDP on average. There are some keywords you have to always mention. I'll tell you. I will highlight this increase. I will also highlight this increase, and I'll highlight this average. Okay. What's happening here? This first word here will always be increase. For now, just take it that way. It will always be increase. The only thing that will change is this one. This one will either be increase or decrease. This one will be increased if the coefficient is positive. But if the coefficient is negative, it will be decreased. So you see here, this coefficient 0.88 is positive. That's why it is increased. If this coefficient was negative, it would have been decreased. So this second one will either be increased or decreased, depending on whether it is positive or negative. But this one will always be increased. It will always be increased. Just think that. Okay, well, at PhD level, when you will be doing non-linear ARODL, then you will discover that this one can be increased or decreased because we have this asymmetric effect, but we are not doing that at masters. So for now, just understand that it will always be increased, right? The next thing you need to know is always mention on average. Because if you look at the data points, maybe there are some cases where increase is causing decrease, and then there are some cases where increase is causing increase, but on average, when you take the average, it is showing you positive relationship. So increase is causing increase. So you have to always mention that it's average. So these three things you have to mention. This is simple regression. When we go to multiple regression, we will still add one more phrase with the partial regression coefficients. So this is how we are interpreting our coefficients. Again, here will always be 1%. Here, this value will always be 1%. This value will change depending on the value you have. This coefficient here is 0.88. That's why it is 0.88 here. In other cases, it might be 0.6, 0. Whatever. So this value will change depending on what you have. But here will always be 1%. This increase will always be increase. And this increase will remain increase if the coefficient is positive, and it will be decreased if the coefficient is negative. Don't forget to mention average. Okay. That's how we interpret coefficients. Now, how do we interpret the constant? Also, with the constant, before interpreting the constant, you must make sure it is statistically significant. If it is insignificant, then you don't even interpret it. But if it is significant, then you can interpret it. With the constant is showing us what the average value of the dependent variable will be if the effects of the independent variables are neglected. So what we'll say here is that without the effect of CPI, the average GDP will be this much, right? So to interpret the constant, we'll say without the effect of mean CPI, the average, again, average, the average mean GDP will be 24.82%. 24.82%. Very easy. But again, it must be significant before you interpret. If it is not significant, you don't interpret. So that is simple regression. Okay, we'll do multiple regression. Before we do multiple regression, I'll mention a few things. So we have R squared, adjusted R squared, F statistic. So guys, what is R squared? This R squared is the coefficient of determination. What do I mean by that? It tells us the explanatory power of the model. Explanatory power of model. What do I mean by that? How much of the variation in the dependent variable can the variation of the independent variable help you explain, right? So in this case, our R squared is 94.7%, which means it has a, because you know R squared can either be, it ranges from 0 to 100. So if it is below 50, it means the model has a really low explanatory power. If it is above 50, it is good. When it's really 80, 90, it is really good. The model has high explanatory power. So because here is 97%, we'll say this model has a high explanatory power, which means 94.7% of the variation in GDP can be explained by the variation in CPI. That's how we explain it. Now with adjusted R squared, it is actually R squared, but it is adjusted. What do I mean by that? Now, sorry? Okay, I will explain. I understand what you're trying to say. Adjusted R squared also shows us explanatory power, but The issue with adjusted arrow squared is that, well, it's not too important in simple regression. It's important in multiple regression. Why? Because there is something happening in econometrics. Whenever you add variables to your model, when you add more independent variables, your arrow squared goes up. Of course, you know a high arrow squared is good. We want a high arrow squared because it tells us the model has a high explanatory power. But you can have a high explanatory power even if your models, even if your variables are useless. So in order to increase your explanatory power, you can just be adding regressors to your model, adding independent variables to your model, right? Because whenever you add a regressor to your model, regressor is independent variable, the arrow squared goes up. Now this regressor you have added, is it useful or useless? Whether it is useful or useless, it doesn't matter, the arrow square will go up. So because of this, the adjusted arrow squared is a kind of punishment mechanism which is trying to tell us the usefulness of that variable that has been added. So if you add an extra regressor to your model, if there are two things involved, and we should not complicate it. If you add an extra regressor to your model, if this regressor is very useful, then the difference between arrow squared and adjusted arrow squared will not be too much. They will be close to each other. But if this regressor is useless, which means it is not very useful in explaining the variation in the dependent variable, then even though arrow squared will go up, the adjusted arrow squared will go down. So there will be a gap. That's why we always look for the difference between adjusted arrow squared and arrow squared. If the difference between them is big, then it means some or most or all of our independent variables are useless. But if the difference between them is small, if they are very close to each other, it means most or all of our independent variables are useful. You understand? But then with simple regression, since we have just one independent variable, adjusted arrow squared is not too important for us because it's not like we are adding another variable. Same thing with F statistic. F statistic is used to perform F test. T statistic is used to perform T test. What's the difference? T test is checking statistical significance for just one coefficient. So you check the statistical significance for the coefficients one after the other. But F test is a joint test. We are checking the statistical significance of all the coefficients together, right? So again, F test is not important for us because we have just one variable. When we go to multiple regression now, you will see that F test is important. Why is F test important? Because you can have a case where maybe some of the variables are individually insignificant, but when you look at them together jointly, they might be significant. Okay. What of these other criteria, Akaike information criterion, Schwartz criterion, and Hanan-Quinn criterion? We use them to compare models. You cannot use them for a single model. That is, on their own, they don't give us too many meanings. But if we are comparing different models, this model and this model, then we can use these variables. The model which has the lower of these variables is better. So let's say you have two models. You look at their Akaike information criterion, Akaike criterion of this model and this model. The one which is lower is the better one. So the model which has the lower of these variables, of these measures, Akaike, Schwartz, and Hanan-Quinn is the better one. Debin-Watson statistic, we use it for autocorrelation. We'll see it later. So Debin-Watson statistic, as a rule of thumb, it should be around 2. If it is around 2, it means there is no autocorrelation in the model. But if it is above 2, it ranges from 0 to 4. If it is around 2, it means there is no autocorrelation. But if it is above 2 or below 2, it means there is autocorrelation. Okay. Since I have just 7 minutes, I will run multiple regression and explain. So for multiple regression, lane GDP, constant, lane CPI, I'll add now lane trade openness. So this is multiple regression, right? You see now we have two independent variables, multiple regression. Again, dependent variable is GDP. You can interpret the coefficients exactly the same, but first of all, check if they are significant. You see, these ones are less than 5, so they are significant, but this one is greater than 5, it's not significant, so we cannot interpret this one. So what we'll say here is that trade openness has no statistically significant impact on GDP. Then here we can interpret this one because it's significant. So we'll say 1% increase in CPI, lean CPI, will cause 0.73% increase in lean GDP on average. Increase because here is positive. With this constant, I'll add something now. With this constant is significant, so we can interpret. So we'll say without the effects of CPI and trade openness, the average GDP will be 25.18%, right? Okay. Now there is one thing I will add while interpreting coefficients in multiple regression. In multiple regression, we have what they call partial regression coefficients. Partial. Partial regression coefficients. We didn't mention this in simple regression because we had just one independent variable. But in multiple regression, we have more than one independent variable. So these regressors are partial coefficients. What do I mean by partial coefficients? It means if you want to know the true effect, the pure effect of one independent variable on the dependent variable, you must hold the other independent variables constant. We saw this when we were seeing partial differentiation at the beginning of the semester. We're doing those maths things. So that's the extra thing we'll add here. So we'll interpret this same way, but we'll add something to indicate that it's partial regression coefficient. So see the way we will interpret this. Of course, we cannot interpret trade openness because it's insignificant. So we will interpret CPI. So what we'll say is that 1% increase in CPI will cause 0.73%. So I'll put here 0.73% increase in lean GDP. Again, it's increase because it's positive. On average, but you have to add something. Provided the effect of lean trade openness is held constant. So that's the extra sentence you must add for multiple regression. But for simple regression, we are not holding anything constant because we have just one independent variable. But with multiple regression, to get the pure effect of one regressor on the regressant, on the dependent variable, you must hold all the other independent variables constant, right? So this is true only if we hold the others constant. So provided it is held constant. So that's all. Okay. So now, R squared again, same thing. Explanatory power of the model. Adjusted R squared. You see, when we did the simple regression, the adjusted R squared was 0.95. It was almost the same. But you discover now that it has dropped. It is 0.94 and 0.95 because so whenever you add a regressor to your model, the R squared goes up. Now, check the difference between R squared and adjusted R squared. If the difference is really big, it means that regressor which you have added is useless. It has no explanatory power on the dependent variable. Take it out. But if the difference is, if they are quite close to each other, then it means the regressor is useful, right? So in this case, 0.95 and 0.94 are close to each other. So it means trade openness is not a bad variable. Okay, now I will show you how to perform F-test and then you can go. We have 2 minutes. Because they should wait, we have 2 minutes. So F-test, null hypothesis. What's happening to my Null hypothesis and alternative hypothesis. F test, since it's a joint statistical test, we are trying to see if the coefficients are jointly significant or not. So you remember with T test, we'll just write here that coefficient is equal to 0. Here, alternative, we'll say coefficient is different from 0. But here, what we'll say is that our two independent variables are CPI and trade openness. So we'll say lean, or let's say coefficient of lean CPI is equals, oh my God, equals to 0, and coefficient of lean trade openness equal to 0. I want to indicate something very important. Coefficient of lean CPI is different from 0, or coefficient of lean trade openness is different from 0. Okay. Why are those people waiting outside when we still have 1 minute? Do they know what can happen in 1 minute? Anyway. By the way, their class is to start at 2:30, right? Not 2:20. So we can finish at 2:29.
No. Sorry, 1 hour.
Okay. Look at something. Please take note of the words, the wordings. Here is and, here is or. With the F test, in the null hypothesis, we use and. In the alternative, we use or. Here, coefficient is equal to 0, and coefficient is equal to 0. So it means both of them must be insignificant. This is insignificant and that is insignificant. But with alternative hypothesis, we need just one to be significant is enough. So this is different from 0, or that is just one. If just one is significant, is enough. Not all of them must be. If all of them are significant, okay, but just one is enough. You understand? And then you perform the test. Again, we cannot use F statistic to perform this test because we don't know the critical value. So we are going to use just probability value. Check this probability value. It is less than 5%. What does it mean? It means we reject this null and we accept this alternative, right? This null is telling us that the coefficients are jointly insignificant. For T test, it's telling you that one coefficient is insignificant. But for F test, it's telling you that all the coefficients are jointly insignificant. And this alternative is telling you that at least one of them is significant, which is one is enough. So because our probability value is 0, which is less than 5, we reject this null. So we reject the fact that they are jointly insignificant, and we accept the fact that at least one of them is significant. Therefore, we conclude that our model is, how do we conclude F test? How do we conclude F test?
It's good, like.
Good. Why? How good? You cannot just say it's good.
It's good. Because we already have our, because it's less than 5% significant.
Yeah, but how do you conclude? It's good, but how do you conclude? Okay, so you conclude that the coefficients are jointly significant and the data fits the model well, right? Or you say the model is of good fit, whatever. So that's how we do F test. So I think I've told you everything. So basically we are done with regression. The only thing which is left is, what's left? Diagnostic tests, heteroscedasticity, autocorrelation, normality, multicollinearity. And there's one extra thing which we did not see last semester, which you will see this semester, stability diagnostics. Let me show you something in a second before you can go. Under residual diagnostics, we are going to check normality tests, autocorrelation, heteroscedasticity. Of course, you know, with correlation metrics and variance inflation factor, we can check multicollinearity. This semester, you did not do last semester, we are going to check Ramsey reset tests. Ramsey reset test, stability diagnostics. I will explain. It's not a problem. So next week we'll do residual diagnostics, stability diagnostics, and that will be all for regression. And then we can start panel data. So I believe that's fine, right? Okay. So you can go. So I'll stop recording now. See you. Bye-bye. Bye. Good? You are sleeping? Ah, sorry. Sorry.
Thank you.
Okay.
But when will we start actually in the course?
Sorry?
When will we start actually in this course?
Where we will start?
Actually in this course.
We started already.
No, but all this from the readers.
It's part of the course.